let's start the class. So last class we looked at the finite element equations, right? So let's go briefly through this. I always like to give an overview of what we did last class. So what you see here, we went through a bar. We said, well, we're going to define some shape functions that are local to those elements, right? And we talked about these special bases. Usually these are called hat functions. They have a really nice property that is a Kronecker delta property. So if you evaluate a function at a node that is equal to 1, but if that function is evaluated at any other node in the mesh, that is equal to 0. And this gives us this nice property that the displacement, right, the degree of freedom at that node is equal to the displacement. But it's because of this Kronecker delta property. So when we're dealing with more advanced finite element formulations, many times that Kronecker delta property is lost. So then in order to get the displacement, even at the node, you have to evaluate the whole finite element approximation, okay? So we look at these functions, and then we said, well, there is this nice property, Kronecker delta. We discretize this problem by using 6 nodes. So we have 5 elements. And then we said, well, since we're going to work with the Bubnov-Galerkin formulation, we're taking both U and W, so the trial solution and the weight function from the same space, so they are represented exactly the same way, and that's what you see here. So that's what you see here. Maybe I change also colors. Yeah. And then, well, we just plugged into our bilinear formulation, and then at the end we obtain our very simple, straightforward system of linear equations that we solve to get the degree of freedom vector U. So what you have on the left here is your stiffness matrix. On the right you have your force vector, and then we have to solve the system for U. And of course, just after the assembly, you cannot solve the system, but you have to apply what? Boundary conditions. Yeah. We also looked at an alternative way to get the finite element formulation. So instead of looking at the bilinear form, right, and just plugging functions, which is really very straightforward, this was hiding something, right? That it was this process of assembly, right? Because in an actual finite element implementation, what we do is we go to every element and we obtain the local arrays. And once we have those local arrays, we just assemble them into the global stiffness matrix or the global force vector. So then we looked at an alternative approach to look at this equation. So we went to an element, just one element, and we evaluated that weak equilibrium in only one element, right? And this is basically that equation that you have here. And if you did that, then basically what we did is that we moved away those W's, right? Because the moment that your weight function is a product of the shape functions times some coefficients, the statement for all W in that space becomes for all vectors W in some like vector space, right? Because your functions are a function of position, and those you know, so those are not unknown anymore. What I mean is that if you look at this equation, I'm going to say that again one more time. This expression for all WH in some space that we call the energy space, the moment that you plug this function, right, since these guys are known, that expression for all WH in some space basically now translates for all vectors W in some vector space. In this case is R2. Right, so it's a vector with 2 components. All right. So we did that, and okay. So then what? Well, we get an expression for the local stiffness matrix and for the local force vector, but then that is only for one element. So in order to consider the contribution of all elements, we look at this process that we called assembly. So we define what it is, the assembly operator, and then we said that the assembly is just a smart way to sum arrays, right? You have to add the contributions at the right place, because 2 neighboring elements, right, would have like the node that is shared by 2 elements. Those 2 elements should add the contributions to that degree of freedom. So that is what we meant by an assembly operation. And that was it. That's what we did last class. Today we're going to start looking at isoparametric formulations. because you can think that if we want to solve a real problem now, we have to discretize our bar, let's say in a few number of elements, but all of those elements are going to have different coordinates, right? So if you want to be smart and not perform a different type of integration for each element individually, you should try to figure out a nice approach to basically do an integration that is homogeneous and it applies the same way to all elements, and that is the idea behind what we're going to do now, which is an isoparametric formulation. It gives you this ability to, no matter where your elements are located in physical space, they are all mapped from one master element that goes from -1 to 1 in coordinate space. And since it goes from -1 to 1, then it's also nice because we have already integration rules that are defined for that line. Okay? So let's do that. Okay. So today we're going to look at isoparametric mapping. So this is going to be our bar segment. And what we said is that there's going to be a relationship between C and X that is defined by our mapping. So and we're going to call this mapping Q. And this mapping goes from some element that we call omega hat to our actual element omega. So this would be our omega element. And this element in 1D we call omega hat. Okay? So the way we express this is just very simply, we use the hat functions because we're going to use a linear mapping between these two. The mapping does not have to be linear, it could be higher order. But for the most part in this class we're going to focus only on linear mappings, even when we go and talk about the p-FEM. So the mapping is defined by shape functions that look like this. So if you look at this function here, when c is equal to -1, we have 2 divided by 2 is equal to 1, xi. So we have the first node, which is right here, and we call this xi, and the other node is going to be called xj. So that is our linear mapping. And what is interesting to see is that now what we have is a function that looks like this. So our x, which is a function of c, is equal to the sum of shape functions phi multiplied by xi. Who recognizes that equation? Yeah?
It's the shape function.
Yeah. So this is a shape function indeed.
Yeah.
And it's multiplying by coordinates in physical space. But who can tell me something about have we seen this somewhere else before?
Discretization of the energies of the weight function.
Yeah, the weight function is written exactly like that.
Yeah.
And the trial solution is exactly written like that.
Yeah.
And therefore, if we express the mapping this is basically mapping geometry. So we have one element in the master space is mapping linearly to a 1D element in physical space through a linear mapping. And because we're using the same shape functions that we're using to approximate the trial solution, that is the reason why this is called an isoparametric formulation. Okay? So that's all it means. Isoparametric, you are using the same type of approximation to look at the geometry and to look at the trial solution. That doesn't have to be the case, as I said. You can have a subparametric or a superparametric. But as I said, for the most part, we will look at isoparametric mappings. And when we go to p-FEM, we're going to keep having the geometry approximated linearly, right? Whereas we are increasing the polynomial order of our approximation space. So we're no longer going to have an isoparametric formulation, okay? Okay. So let me just summarize that. Okay, so if you have a mapping, you can also think of an inverse mapping. Where given an x value, you want to find out what is the value of c. So here we go from omega to omega hat. And this is given by okay. And as we said earlier, all of this is mostly used for integration, so that we have a uniform way to perform numerical integration in our elements. So let's see how we use these concepts. So if we have an integral between xi and xj of some function of x, dx, this is going to be transformed into an integral between -1 and +1 of a function that is still a function of x, because we're just changing the limits of integration, and then j dc, right, where j is called the Jacobian of the transformation, right? And we can obtain this very straightforward because, well, the x so what you see here, the length of that element divided by 2 is what we define as the Jacobian. Yeah, but we're still not performing really numerical integration. So we have to transform that integral into a sum where we go from I equal to 1 to, let's say, the number of Gauss points, and then we basically evaluate that function, let's say, at some Gauss point, and then we have the weight and the Jacobian also evaluated at that Gauss point. Yeah, so I'm gonna put here evaluated at CI. And this is the way we always perform numerical integration in finite elements. So we never do exact integration, except for a few cases where we know how stiffness matrices are. Like, for example, if you're working with triangular elements in 2D, those are linear elements, so the derivatives of those are going to be constant. So your bilinear form, normally, if you don't have very fancy change in material properties inside those elements, you can actually get a closed form expression for your stiffness matrix. Yeah, but for the most part, when we perform numerical integration over elements, we do it this way. We do numerical quadrature. So we evaluate whatever needs to be evaluated at discrete points inside your domain, and we do the integration by Gauss integration by multiplying by weights and by the Jacobian and so on. Yeah. So for example, if we take the stiffness matrix, right? So if you remember, and we express our bilinear form, it was going to look something like this. We have EA, and then we have the phi, which was a vector. A vector of which size? 2 by 1. The x, so the transformation of that is very straightforward. We say, well, we just have to xi, xj, yeah, EA, and now we have an issue here because now our shake functions are they are a function of c coordinates, so we have to apply the change rule. So we have to do derivative of c dx, and you see how our mapping gets there again through the Jacobian. And I'm missing here transpose. Yeah, so what you see here is that these two guys, this is equal to 1 over j. Okay, and then of course we further change that to evaluating that expression at a few number of Gauss points. So EA d phi like this. And of course, all of that has to be evaluated at some integration point. So that's the way we perform the numerical quadrature, right? We take whatever expression we have and we evaluate that expression at some points in our element, and we just add. It's a summation. And of course, we have to be careful, because if whatever we want to integrate is a function of x, right, then there is nothing to do there anymore. But if it is a function of c, since what we're interested is indeed in physical space, we do have to apply this change rule. That's why in this expression here, you see that because of my shake functions now are a function of the master element psi, then I have to apply and change rule. And then the mapping, the Jacobian of the transformation gets there again. Okay? All right, so that's all I wanted to say about this. So if you use, let's say you have a linear function to integrate numerically, how many Gauss points would you use? 2. Another guess?
As much as possible.
No. Who has seen numerical quadrature by, let's say, Gauss integration, Gauss Legendre or Gauss Lobato rules? Yeah? Only one? Come on, guys. 2. Who else? Okay, so let me ask you, if I have n integration points, does someone remember what is the exact polynomial interpolation order that I can integrate? Exactly? Huh? Almost. 2n minus 1. So if I have one integration point, what I can iterate exactly? What is the order of a polynomial? 1. So a linear polynomial would need 1 integration point. Okay. So let's look at now at our 1D stiffness matrix, because we said, well, we have linear elements, right? The elements are linear, so the shape functions are linear. So the derivatives are constant. And now I'm doing the product of the derivatives of the shape functions with themselves, which is constant times constant, is constant. So how many Gauss points I need? Huh? How many? Come on, how many? 1. In fact, because everything is constant, we do not perform integration. And if you remember, you may remember that, well, this is K. Normally, what we have is EA over the length of the element, and this is what you get. We don't even perform integration at all. Okay. But okay, that is because we are not really. We assume that E is constant, that A is constant as well. So if that is no longer the case, you have to perform some integration, and you're going to have to see how those functions behave, so that you choose properly the number of integration points. Okay. And in the problem of the project, the first project, right, you're going to have a complicated right-hand side. Right? It's a complex equation, so you're going to have to be very careful with the number of Gauss points that you take into consideration. And that's some insight that I want to get from you. You know, how many Gauss points you had to use, and how you managed to find how many integration points you had to use. Okay, so are there any questions about this? Yeah.
The integration boundaries on the right side need to go from -1 to 1 is enough.
Yeah. Yes. Thank you so much. Yeah, this is wrong. Thank you so much. Anything else? Okay, so we stop here. We're stopping a bit earlier. So we meet in 10 minutes, and because I need a lot of time to go through the heat equation in 1D and in 2 and 3D. Okay? So let's stop here.